Welcome back. Let's continue with our backpropagation example in neural networks. As a reminder, Python files and code explanations can be accessed in the free Udemy tutorial Vehicle Suspension Control 4 PID Tuning with AI TD3. Go ahead and enroll in the course. The link is in the description. Also, note that the free coupons that I offer for that, they have limitations in terms of time and the number of enrollments. However, don't worry, I will be renewing them periodically. In the last video, we had a fully connected neural network with weights and biases. We had the inputs, I1 and I2. We gave them these values, and then we wanted the network to map them to concrete outputs chosen by us. We wanted our outputs to have these values. For that, it was necessary to apply some learning algorithm to find the correct values for the weights and biases to get these outputs for these inputs. But remember how we propagated from inputs to outputs. We used these matrix vector operations in order to achieve that. This one here mapped the input neurons to the ones in the hidden layer, and then on the right, the hidden layer neurons were mapped onto the output layer neurons. So we first had H vector equals all this, and then the O vector containing the output neurons. We obtained them with this expression. If we now substitute this H vector with this expression, I will have this result. If I expand it, I will have this result. This will be our new weight matrix that we can call like this. Then this will be the new bias vector that we can call like this, BOH. It means that we can write the output vector as a function of the input vector directly. However, this here, it's almost a linear system. You have a linear subsystem here, and then you have a bias here. If you didn't have the bias, you would have a truly linear system. The bias makes it nonlinear, but the only nonlinearity here is simply this constant offset, which is the bias. So, as a side note, to have a truly linear system, you have to obey something called the superposition principle, which means that if you have a system, y vector as a function of x vector, where y is output and x is input, then if x1 gives you y1 and x2 gives you y2, then the system is linear when the addition of these two inputs, x1 plus x2, gives you the sum of the two outputs, y1 plus y2. That's the superposition principle. And so, if for instance you have this system, where A is an n by n matrix, and then both x and y, they are n by 1 vectors, then if y1 equals A times x1, and y2 equals A times x2, then from here, we have the following. A times, and then instead of x, I will have x1 plus x2, so this is my new input. That will give me a new output, which will be this plus this. You can see that this one here, that's y1, and this one here, that's y2, which means that the superposition principle holds here. That's because we had no bias in this system. However, let's add a bias vector now. Let's say that I have a system y equals A times x plus b, where b is a constant n by 1 vector. In that case, y1 would be this, y2 would be this. However, if I now insert a new input into the system, which is the sum of the previous two inputs, my system will then look like this, or I can also rearrange the terms. In this rearrangement here, this would be y2, but of course this one would not be y1, or if I choose this arrangement, then this would be y1, but then this one cannot be y2. Either way, this expression does not equal y1 plus y2. From here you can see that the superposition does not hold. Therefore, a bias introduces nonlinearity. All that means that the neural network that we have here, it can only work when the relationship between the input and the output vectors is either linear, where the bias is 0, or the relationship is nonlinear, where the only nonlinearity is some constant offset represented by that bias. In that case, it's possible to find the weight matrix and the bias vector using some numerical algorithm that maps the given inputs to the desired outputs. However, if the relationship between inputs and target outputs contains other types of nonlinearities, and there are many of them, then the neural network that we have will not be able to find the necessary weights and biases to even approximately map inputs to target outputs. That is why neural networks also have activation functions. Without them, neural networks would be quite useless. In our network, we will introduce the activation functions in the hidden and output layers. Once you calculate the h vector, which consists of h1 and h2, before you use it to compute the elements of the o vector, you will first apply a function to it that will give you new values for h1 and h2. So you will have h1 asterisk and h2 asterisk. So I calculate this h vector here. Using this transformation, I then obtain h asterisk by applying some function to h. Then, when I calculate the o vector, I need to make sure that I'm using h asterisk here and not h. And once I have my o vector, I calculate o asterisk. In this way, this function f, that's the activation function. These activation functions, they might be the same, or they may differ, depending on what works best. Sometimes, activation functions are not applied to output neurons. However, in our example, we will apply them to the output layer. It also means that now, our target outputs 0.05 and 0.95 will not be O1 and O2 respectively. They will be O1 asterisk and O2 asterisk respectively. The question now becomes, what should that function be? The answer is that it should be a function that can enable a neural network to approximate any nonlinear function. Ultimately, we want neural networks to be universal function approximators. No matter the relationship between the input and the output, we want the network to be able to approximate it. If you have pictures of dogs and cats, and your inputs are pixel intensities, that for instance in a grayscale image would be between 0 and 255, then you want your network to properly map these pixel intensities to the right animals. You want to train the weights and biases of the network so that it learns to differentiate between dogs and cats. And so, the activation function should enable the network to approximate any relationship you throw at it. Some of the most popular activation functions that allow neural nets to be universal approximators are the following. ReLU, which stands for rectified linear unit. So if this is the domain and this is range, then the function graph would look like this. Mathematically, it would look like this. We will use it in TD3 as well, in PID tuning. Then another popular activation function is sigmoid, which can also be called logistic, and this function only has a range from 0 to 1. Mathematically, this function is represented like this, or like this, and this is the one that we will use here in this example. And then hyperbolic tangent is also quite popular. Graphically, it would look like this. Its range would be from -1 to 1, and then mathematically the function would look like this, and we will also use it in PID tuning in the TD3 algorithm. But of course, there are others too. For different applications, different activation functions are used depending on what works better. As mentioned before, in our backpropagation example, we will use this sigmoid function. It means that if our inputs are 0.1 and 0.2, then the path to computing the outputs would be as follows. The first step would be calculation of h1 and h2. Once we have them, we have to calculate h1 asterisk and h2 asterisk, and we're going to do that by applying the sigmoid activation function to h1 and h2. Once that is complete, we will calculate O1 and O2 using h1 asterisk and h2 asterisk. It's important that you use the activated neurons. And finally, in order to calculate O1 asterisk and O2 asterisk, you will again apply the activation functions. You will so-called activate the output neurons, and our target outputs will be these ones here. In the next video, let's see how we can use backpropagation to find the weights and biases that would give you these desired outputs to the given inputs. Thank you.